Hey ChemStars, welcome back. Let's look at Level 1, pages 10 and 11, looking at some more mass-to-mass conversion problems. So our objective for this set of problems is that I can use chemical equations to perform mass-mass calculations using Bca tables. So here we've got some practice. We've taken away some of the supports, and now you are going to be setting up your own Bca tables. Number 1, how many grams, I probably should turn on the shade here so we can focus on the one problem at a time. How about pink today? Okay. Number 1, how many grams of H2 hydrogen are needed to convert 5 grams of O2 into water? So let's look at what we know. We need to balance the equation, Bca. Before we start, we have no product. We're going to create product. We're going to use up reactants and have exactly the right amount, so there'll be none left over. So how many grams of H2 are needed to convert 5 grams of water, or 5 grams of oxygen into water? So take our 5 grams of oxygen and divide by the molar mass to get how many moles of oxygen there are. So you get your molar mass in the periodic table. Oxygen 16 times 2 for O2 is 32. And so we need to take 5 divided by 32, and we get 0.15625. Oops, wrong color. Let's try and be consistent here. 0.15625, and that's how many moles of oxygen that we have. So we're going to have that much when we start, 0.15625, and how much of it we're going to use up? All of it. So we're going to use up all of that 0.15625, and there'll be none left over. So how much hydrogen am I using up? I'm using up that coefficient, which is the 0.15625, times the mole ratio from our balanced equation. Remember that we only ever pull our mole ratios from up here. Okay, this is where all the mole ratios come from. This is our recipe. So their ratio is 2 to 1. So we need to take this number times 2. So we really used up 0.3125. We used up 0.3125 moles of hydrogen. So if there's none left over and that's how much we used up, how much must we have started with? Well, that number, 0.3125. So right here, 0.3125. And remember, the Bca table is always moles. So that's how many moles of H2 we used. But do they want to know moles? No, that'd be too easy. So we've got to take that number out of the Bca table, and we're going to take our 0.3125 moles of H2. We want to take that over 1, and we want to cancel out moles and go to grams. You probably have this memorized by now, but let's just double check. Molar mass of hydrogen, 1.01. But this is H2, so that's going to be 2 times 1.01. That'll give us 2.02 grams per mole. So 2.02, okay. 2.02. So take that number in your calculator still, times 2.02, and we're going to get 0.63125. 0.63125. That's how many grams we have, and last thing we got to do is check sig figs. There's only 2 in the problem. That means our answer can only be precise to 2 sig figs, so 0.63 grams of hydrogen are needed. Good. Any questions? Make sure you reach out to your teacher. And let's move on to question 2. Okay. On this one it says, determine the mass of hydrogen needed to convert 233.0 grams of oxygen to hydrogen peroxide. So our equation has changed. Now we're taking hydrogen plus oxygen and getting hydrogen peroxide. So let's take a look at what we know on this problem. Coefficients are all 1. Now before we start, okay, no product, we're creating it, we're using up the reactants. Here my ratio is 1 to 1. So 233 grams of oxygen, we need to figure out how many moles that is. O2, if you check the periodic table, oxygen is 16, so O2 must be a molar mass of 32. So we're going to take 233.0, divide by 32 grams per mole, and that tells us that we have 7.281, I'm just going to say 7.28 moles of oxygen, but keep that number in your calculator. So how much of it are we going to use up? All of it, 7.28. This is my limiting reactant. Technically, I'm running out of both things, but I'm using all of it up. So how much hydrogen will I need? Well, I'll be using up that same coefficient, the 7.28, times the ratio of the unknown to the known, 1 over 1. So if there's none left over, that's my 0 right here, there's none left over, and I used up 7.28, how much must I have started with? 7.28 moles, okay? But the problem, they want grams, of course. We're on the gram to gram worksheet. So we need to take that 7.28 moles of hydrogen, and we need to multiply by the molar mass, just like we did in the previous problem. So make sure that whole number is still in your calculator, times 2.02. H2 is 2.02. 14.708. So we've got 14.708. Now in this problem, how many sig figs? 1, 2, 3, 4. 1, 2, 3, 4. So look to the right. The 8 will round that 1 up. That gives us 14.71 grams of H2. One more problem on this page. Okay, we need to calculate the grams of carbon dioxide produced when this exact amount of hexane, 23.44 grams, burns in air. We're going to say the air is excess. Remember, that's O2. Write out your own equation. This is a combustion reaction, so the hydrocarbon plus oxygen will burn. Oops, remember to put your deltas over there. I think I've forgotten to do that in these videos, saying that there's some kind of spark or ignition. It'll burn and produce carbon dioxide and water vapor. They're being sneaky. They didn't tell you water in the problem, but you should recognize from chapter 8 that water vapor will always be a product. Here's my balancing. Now, is this okay? Kinda yes, kinda no. So I have the right ratios, and if you notice, like when I'm doing my Bca tables, I'm only using the coefficients right here, and it's all about the ratio of the unknown to known. So if you want, you can just leave this half balance, like I call it. If it makes you feel better, go ahead and double them all so you have whole numbers, but you're going to get the same answer no matter which way you choose. Okay, so first thing is, let's take a look at the Bca table. Before I do any work, do you understand how I have this set up? If yes, good. If not, go back and rewatch some of those lecture videos. Okay, molar mass of hexane C6H14 is 86.20. Nope, I didn't even write that one on here, I don't think, but hopefully you can trust me on that one. Or let's double check and add all those things up. So we need to take 23.44, divide by 86.20, and we get 0.2719. So 0.2719, and that's going to be my moles of my hydrocarbon. So before the reaction, I have 0.2719. That's what I'm running out of. I'm using up all 0.2719, and there'll be none left over. That's my limiting reactant. Okay. They want to know about CO2. I'm going to ignore everything else and just focus on getting the CO2 work done here. So how much am I creating? This is my recipe, but here's my actual ingredients. So that coefficient, 0.271 times the ratio of carbon dioxide to the hydrocarbon. So that's going to be 6 over 1. Now, if you doubled it, you'd be taking 12 over 2. Well, what's 12 over 2? 6 over 1. It comes out the same, you see. So take that number. We're leaving the whole number in our calculator. Times 6, and we're going to get 1.6315. 1.6315. That's how many moles of CO2 there are, but of course they don't want moles, they want grams. So we got to multiply by the molar mass, which you get using your periodic table. And so take that number times 44.01. Should be a 1 right there. And you will get 71.80, and what's my next digit? 804. Okay, because look at the original problem. They gave us 1, 2, 3, 4 sig figs. 1, 2, 3, 4 sig figs. Look to the right. So it's going to be 71.80 grams of carbon dioxide produced. Good. We're done with page 10. We got one more page to go here. So flip to page 11. This one's longer. I've got some of them set up for you already. And let's just go through these. So number 4. Carbon will react with zinc oxide to produce zinc and carbon dioxide. How many grams of carbon dioxide will be produced if 12.9 grams of zinc is completely reacted with excess carbon? Write out your own equation. Well, I've done some of that for you. In a quick test, what type of reaction is this? We've got a single element kicking out a different single element. That looks like it's going to be a type of single replacement. You might be like, oh, but look, carbon's trading places with a metal. Is that okay? Well, That's what happens here. Remember, carbon's almost kind of a metalloid. It gets kind of close to that stair-step line. Okay, so first step is set up your Bca table, excess carbon, no products. How many moles of zinc are we starting with? Well, we've got to convert by dividing by the molar mass, plug that in, we use all of it up. That's our limiting reactant. They want to know about CO2. I'm creating that number times the ratio of carbon dioxide to zinc, which gives me this number of moles right here. They don't want to know moles though, they want to know grams. So multiply by the molar mass, and you end up with 3.49 grams of CO2. Now I already had a lot of that done. If you've got more questions, make sure you contact your teacher. I'll start from scratch on number 5 with you and show you all the steps. So it says, how many grams of hydrogen will be produced if 34.0 grams of calcium hydride reacts with excess water to produce calcium hydroxide and hydrogen? So we got to start with that equation first. So we're going to have some number of calcium hydride reacting with excess water, H2O, and that's going to produce calcium hydroxide, CaOH2, plus hydrogen gas, plus H2. Okay, remember, this is going to be our recipe, our balanced chemical equation that we'll pull all the mole ratios out of. Is it balanced? Well, here's what we can always do to help. Instead of writing water as H2O, especially when you see hydrogen by itself, we can try writing it as HOH. Let's see if that helps us with our balancing. So times HOH. Now I can see right here, first off, I have 2 hydroxides. I need to get 2 hydroxides. Okay, that makes the hydroxide good. There's 1 calcium, 1 calcium. That seems fine. Now we can focus on the hydrogens. H2, now just the H2 here because I've already balanced the OH, so H2, that's 4 hydrogens. Put a 2 in front, that gives me my 4 hydrogens. We are all balanced and fill in a 1. So Bca, before, change, after. Let's divide up our reactants and our products. So before the reaction starts, how much calcium hydride do we have? Oh boy, 34.00 grams. So we got to do a little bit of work, 34.00 grams over 1, and we want to get rid of grams, and we want to go to 1 mole. CaH2, go to your periodic table. We're looking for let's try that with a different color. CaH2, here's calcium, so 40.08 plus 2 times 1.01, so 40.08 plus 2.02, 42.1. So that's our molar mass, so 42.01. Oh, wait, 42.110, sorry, 42.10. So take your calculator, which I just closed. Oh boy. So 34 divided by 42.1. We're going to get 0.8076. So 0.8076. And that's going to be my moles that I can plug in here. So 0.8076. Before the reaction starts, how much water do I have? Excess. I've got a whole lot. Before the reaction starts, no products. You don't have brownies until you make brownies. So before the reaction, no products. During the change, what's going to run out first? The 0.8076 or the excess? Well, you're definitely going to run out of the 0.8076. And so during the change, it's all used up. There's none left over. That's your limiting reactant. Now, it doesn't ask me about how much water is used up, so I'm just going to kind of skip that for now. What they want to know is they want to know grams of hydrogen. So this is what I'm going to zero in on over here. So I'm going to be creating 0.8076, that's my coefficient for my limiting reactant ingredient over there, times the ratio of the unknown hydrogen to the known limiting reactant. So take your number in your calculator, it should still be in there, times 2. 1.615. We got 1.615, and that's how many moles of H2 we've produced. But they want to know grams, of course. So we've got moles of H2, put it over 1. We want to get rid of moles. H2, the molar mass is 2.02 grams. So take that number times 2.02, and you're going to get 3.2627. 3.2627 grams. Last step, look for sig figs. 1, 2, 3, 4 in the original problem. 1, 2, 3, 4. So that 7 will round your 2 up. And our final answer is 3.263 grams of hydrogen will be produced. Okay. 2 more problems. You're doing great, guys. Number 6. This one I did a lot for you already. Nitrogen can react with hydrogen, N2 and H2. Remember, have no fear of ice-cold beverages. All those elements are diatomics. To produce ammonia. You've memorized ammonia, NH3. How many grams of nitrogen will be needed to produce 1.88 grams of ammonia? Okay, so first things first, write your equation. N2 plus H2 equals NH3. When you see a lot of 2's and 3's, think about going to 6. So over here, we got to get 6 hydrogen. There's my 6 hydrogen, N2, N2. Easy peasy. They want us to solve for how many grams of nitrogen, so we don't know how many grams of nitrogen. We don't know this number yet. We're working backwards to produce 1.88 grams of NH3. So we're coming over here, and you want to divide by the molar mass, which you get from the periodic table. So remember, go to your periodic table for NH3. We have, oops, didn't want to do that. I was trying to highlight. So for NH, oh wow, you can't highlight like way. Anyways, oh now I'm messing it all up. Here we go. NH3. Oh, we're struggling together, guys. NH3, 1 times nitrogen plus 3 times hydrogen gives you 17.04 grams. That's where this number came from. So we plug this number into the end of our Bca table. So this came from our grams. Now, we started with none, and I created this much. We're trying to solve for our unknown question mark, okay? Oops, that's the wrong color. We're trying to solve for our unknown question mark right here. So the coefficient from my nitrogen is going to be equal to the ratio of ammonia to nitrogen, so times 2 over 1. So question mark times 2 equals this number. Isolate and solve. Here is your question mark. So we plug that number in, and that's how many moles of nitrogen that we used up. But does the question want to know about moles? No, it wants to know about grams. So take your moles times the molar mass, which is 28.02, and you're going to end up with 1.545, but rounding for 3 sig figs is going to be 1.55 grams of nitrogen. See, it's not so hard to work backwards. Just take your time and identify what you know. Last problem, and then we are done for today. Okay, number 7. Hydrogen iodide reacts, so let's get our color coding started here so we can see how everything cancels. Hydrogen iodide reacts with oxygen gas, remember it's going to be a diatomic, to produce water and iodine, another diatomic. Okay, let's just stop there and get our equation written out. So, hydrogen iodide, H plus, I1 minus, it's going to be HI for our formula, reacts with oxygen, oxygen's diatomic, O2, to produce water, H2O, plus iodine. Remember, iodine is solid, but it's still a diatomic, I2. So this is my recipe. I need to balance it so I can pull my mole ratios out of it. So we have O2, and we've got I2. Well, we got to fix the oxygen first, okay? So I want to keep that O2, but I have to get O2 right here. Oxygen's good, but that just gave me 4 hydrogen. How do I get 4 hydrogen? Put a 4 in front. Well, that just gave me 4 iodine. Now put a 2. 4, 1, 2, 2. It's balanced. What would happen if you had like 4, 2, 2, 2? Reduce. It's always the simplest whole number ratio here. So we've got our reaction. Now let's get our Bca table going so we can analyze this reaction. Separate your reactants from your products, and let's identify what we know. Before you make brownies, you don't have any. So before we have the reaction, there are no products. And we'll be creating some positive numbers of those when we're done. Okay, reacts with oxygen gas. So they want to know how many grams of oxygen. Oops, wrong color again. They want to know how many grams of oxygen, so question mark, grams of O2, are required to react completely with 9.76 grams of hydrogen iodide. Before I do anything else, that key word right here, the completely, that is telling me that there is going to be nothing left. Each one will be completely used up in the reaction. So I'm going to have some number of hydrogen iodide. That's the coefficient I'm going to get from the 9.76. And I'm going to be using up that same number times the ratio of hydrogen iodide, oxygen to hydrogen iodide. What I'm trying to solve for is this number right now. Okay, so 9.76 grams of HI. So 9.76 grams of HI over 1. We want to get rid of grams, and we want to go to 1 mole. That means we've got to go to the periodic table. So let's find HI. Okay, H is right here. Iodine is right here. So we've got to take 126.9 plus hydrogen, 1.01, 127.91. So 127.91. So how many moles of HI am I actually starting with? We got to take the 9.76, divide by 127.91, and we're going to have 0.0763. 763. And that's how many moles of HI I have to start. Okay, so this number, I'll try not right over top of everything, this number goes in right here. So 0.0763 moles of HI. How much of it do we use up? If it's completely reacted, we use up all of it. So minus 0.0763, and that's going to be none left over. Now we can focus on the oxygen part. Okay, so we're going to be using up that same number. That's our limiting ingredient right here. We're using up that 0.0763 times the mole ratio, the unknown oxygen to known hydrogen iodide. So in our calculator, we've got to take this number and divide it by 4. So this term right here is actually 0.019075 blah, 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 blah. If there's none left, and this is how much I used up, how much must I have started with? That same number. So 0.019. 0.019. And that's my moles of O2. But do they want moles of O2? No, they want grams. Okay, so we're taking our 0.019. Now keep the whole number in your calculator. So that's 0.075 moles. Put that over 1, and we want to get rid of 1 mole, and we want to go to grams. Remember, it's O2. So on the periodic table, it's not just 16, it's O2. 16 plus 16. So 32.00 grams per mole. So take that number in your calculator, times 32, and that gives us 0.6104. And that is how many grams of oxygen were needed to completely react it. Have I considered sig figs? Let's go back and check. 1, 2, 3. Placeholder, decimal is present. Count from the first sun, 0 in the Pacific. So 1, 2, 3. That 0 is significant. So 0.610 grams of O2. Are there 3 sig figs in my final answer? Yes. Here they are right here. Okay, that brings us to the end of page 11. Great work today, ChemStars. I'm proud of you. Keep on